Okay, welcome to the third video in the logs and exponential topic. Today we're going to look at the exponential function and in particular cases involving e to the power x. Okay, so there's four things we want to be able to do today. Firstly, use formula involving the exponential function e to the power x. We're going to solve equations with unknown as within the power. Solve equations involving the exponential function e to the power x, and solve problems involving the exponential function e to the power x in context. Okay, so last video what we finished with was looking at lots of solving logarithmic equations. Today essentially we're going to look at the exceptions, or exceptions where we can use a different method to do it. Firstly though, I'm going to introduce you to a new number, excitingly. Now, like pi, e is a number, a rational number that has no it doesn't stop. Okay, it carries on and on and on and on, and it's got its own value that never changes. In this case, or in all cases, e is 2.718 and so on. Okay, that's called the exponential function to base e when you raise it to the power x. Okay, now you'll find it on your calculator in yellow above at the top right of your Casio calculator, above a button that says ln. Okay, that's where we go to use it. Okay, and it's really linked close to a lot of things in nature like bacterial decay, population growth. This exponential is linked close in there. Now, this slide here is essentially getting used to using that button and using your calculator to use E. Okay, so what to do, I've told you the button is, see if you can find me e to the power 1.2, 5e to the power negative 4 that is, and then working in the context in question 2 as well. So pause the video and go nuts with that. Okay, so what you should have found is if you do e point to the power 1.2, that will get you 3.32 and so on. So just let's call it 3.32. Okay, if you do 5e to the power negative 4, it gives you 0.09157, or let's call it 0.092. Okay, so if you're getting in, that's you're happy using this function. And then secondly, and I've picked this example because it looks a lot like the ones that come up in past papers, a little bit easier than that, just because of straightforward substitution. But here, the massive radioactive material decays according to the formula. M is equal to m naught e to the power 9 is 0.02 t, where m naught is the initial mass and t is the time of years. Okay, so m naught here is the initial mass, which means the mass at the start of that time, and find the mass after 10 years, and the initial mass is 300. Okay, that's quite common parlance, if you like. To find this mass, essentially, you're going to use this formula, same way you've been using any formula, like the speed, distance, time, or the volume of a sphere. We're going to sub in m naught, the initial mass, which is 300. Then we have e to the power minus 0.02 times t, which is 10 years. Okay, so you go to your calculator and you type that in. It comes out with the answer 245.6. Okay, 245.6. We're talking about grams, so 245.6 grams after 10 years. Okay, so that's using your e function. Okay, now just like any other exponential function, whether it be 4 to the power x, 5 to the power x, or e to the power x in this case, it has a logarithmic inverse. In this case, though, we tend to use a special inverse for the natural log. Okay, they're called natural logarithms. Log e to the base x is ln x, like here. Okay, that's logarithmic natural, because it was born in France. Okay, we can use the ln button in a calculator just below where you've been using your e button to use that and to calculate different things. Now, this is going to help us in two ways. One, well, any log would help us in two ways there, but we tend to use the natural log where as a kind of default. Two situations. One, if we have problems like this where the x, the variable we're trying to find, is within the power, logs, using our log laws, lets us take it out of the power. And then what we're going to do is just going to talk about it slightly differently, but solve equations involving ln and e in there. Okay, so first of all, 1a here, solving the equation 3 to the power x equals 56. That has a x in the power, so we need to get out of the power, and that's where logs come in so useful. Okay, because if we can take a log of both sides here, ln 3 to the power x is equal to ln 56. Our laws of logs means that we can take that x down to the front and get rid of our x in the power. Okay, then you're multiplying by the natural log of 3. So all we need to do is x equal to ln 56 divided by ln 3. And I'll just carry on here. I'll probably pause the video and buy myself a bit more space in a minute. But you're doing ln 56 in your calculator, just divided by ln 3, so that's 3.66. Okay, so that log lets you get that x out of the power and solve it easily. Okay. Okay, in part B as well, same idea. We've got our x's in the power. So we're going to take a natural log of both sides. So ln 5 to the power 3x minus 2 is equal to ln 30. And then the power can come down the front. So it's 3x minus 2, which will have to be in a bracket now because all of that's multiplying by ln 5 is equal to ln 30. So 3x minus 2 is equal to ln 30 over ln 5. So add 2, divide by 3. So x is going to be ln 30 over ln 5, add 2, all divided by 3. And I'll just calculate that. Okay, so that's 1.37 when you type it in your calculator. Now these aren't very common. There was one a couple, I think about 5 or 6 years ago that came up as the last question of paper 2. But if you have unknowns in your powers, logs let you take them out. Okay, now it can be any log. We tend to use ln as a kind of default. If it's stated in the paper, in your paper as something else, then we can do that there. Okay, now we're going to look at something that's much more commonly asked. It comes up much more frequently, working with equations involving ln and involving e. Okay, now we're going to think of this slightly differently, and it's just for ease more than anything else. The mathematics behind it is exactly the same, but when I teach this, I like to teach it just in terms of cancelling out when we teach ln and the e's. Okay, so what I want you getting used to that ln x and e to the x are inverses. So ln and e's cancel each other out the same way that adds cancel out subtracts and the times these take away cancel out divides. So for this question here, we're looking to solve the equation ln x equals 4. Well, if we want to get to x, we need to cancel out this ln, and we're going to do that by doing an e. So x is really e to the power 4. Okay, now that is the same way that we've solved logs before, but just think from my experience, kids find it a little bit easier working with this balance. Okay, so e to the power 4 is 54.6, and that's our solution to that equation. Okay, so 54.6. Okay, same here. If you've got e to the power 3x equals 25, wait there again a little bit bigger, e to the power 3x equal to 25. To get to the x first, we need to cancel out the e. We're going to do that by using the natural log. So 3x equal to ln 25, and then we can just do ln 25 divided by 3 will give us the x. Okay. Okay, so x in this case is 1.07. Okay, so for log equations like before, single log cancel. When you're using your ln's and you're using your e's, just be cancelling out by the inverses. Okay, now these come up most of the time in exams in this sort of format. Okay, with a story related to something like half-life or decay or population growth. Okay, but the mass g grams of a radioactive sample after time t years is given by the formula g is equal to 100 e to the power minus 3t. What is the initial mass of radioactive substance in the sample? And then find the half-life of the radioactive substance. Okay, so 2 questions here, and these questions are brilliant. I love these questions. Okay, because they've been using these skills since primary school. Speed, distance, time, area of a rectangle, volume of a sphere. They're just using a formula. Okay, getting a formula and substituting them. Okay, so for part A here, we've got the formula G is equal to 100 e to the power minus 3t. Okay, the initial mass of the radioactive substance, or at the start, at that very start, t has got to be 0. So if we substitute that in, we'll be able to calculate the initial mass. Okay, so the mass at the start is going to be 100 e minus 3 multiplied by 0. So minus 3 multiplied by 0 is just 0. E to the power 0, well, anything to the power 0 is 1. So 100 times 1, initial mass is 100 grams. Okay, and that will always work. Your initial mass will always be in front of your e, because if t in there is 0, it automatically makes it exponential to the power 1. Okay, so that's where the initial mass is. Now B is a little bit trickier. It's not just a sub in and calculate, it's a sub in and solve. Find the half-life of the radioactive substance. Okay, now for those of you who have not done physics extensively, half-life is the time it takes for a substance to half in mass. Okay, so when you're asked for a half-life, you're asked for the time. And the time it takes for the substance to half in mass means we want to know how long it takes for the mass to go from 100 grams it started with to 50. So if we swap in 50, we'll have an equation that we can solve. So we just need to cancel out that 100. Well, I'm going to divide by 100. 50 divided by 100 is just a half. Oh, look, half-life. Isn't maths wonderful? Okay, we know we're wanting to times it by a half, so e to the power minus 3t has to be a half. Then you're cancelling out that e by doing a natural log, and then you're going to find the time by dividing by -3. So the time is going to be ln 0.5 divided by -3, which is 0.23. Okay, so in this case it's 0.23 years. Okay, now that's the format it always takes these questions. Sub in and calculate, sub in and solve, a mixture, a variety, or one of the two of those things. Okay, everything else is just kind of window dressing in words. That's just what we're doing here. Okay, so next question, question 3. The world population in billions, T years after 1950, is given by P is equal to 2.54 e to the power kt. Okay, so in 1960, the world population was 3.035 billion. Okay, so firstly, the world population in billions, so that's P. T years, so T is the number of years after 1950, and K, well, K is just a constant. Okay, so to find K, essentially I need to get rid of everything else in there that's not a number apart from K. So I'm given this information here. Okay, if it's 1960, that means it's 10 years after, and the population was 3.035 billion. So I can sub that information in. 3.035 is equal to 2.54 e k times 10, or 10k. And then you just go and solve. Okay, you need to cancel out that 2.54. We're doing 3.035 over 2.54 is equal to e to the power 10k. I'll just go over to this side here. Then we need to cancel out this e, so it's ln of 3.035 over 2.54 is equal to 10k. And then divide by 10 means ln of 3.035 over 2.54, all divided by 10 is equal to k. So k is equal to, okay, 0.026. Okay, 0.026. Okay, now we can move on to part B. Give me 2 seconds, I'll just turn my use. Okay, so we found k is equal to 0.026. Find in the nearest year the time taken for the world population to double. Okay, now that's double from the initial 1950. Okay, so P we now know is 2.54 e to the 0.026 t. And for that population to double, we know the initial population here is 2.54. Okay, so we're looking for it to become 4, rubbish, 5.08. Okay, now there is situations where they do not give you that initial mass or the initial population at the front, they just give you as P naught. Okay, that's fine, you can just make it up then. Okay, so say P naught was 100, we wanted to become 200, say. Okay, that's quite common, but you'll do lots of practice of that and you'll see lots of examples with that. Okay, now we're ready to solve. We've picked the population doubled, divide by 2.54, so 2 is equal to e to the power 0.26t. Look at that again, we're looking for it to double, so we want the e, the exponential, to be 2. Then we're getting rid of that e by doing ln2 is equal to 0.026t. So t is equal to ln2 divided by 0.026. So the time taken is 26.7, which means 27 years to the nearest year. Okay, now apologies for the length of the video. You'll notice very quickly when you do these past paper examples, or you do these examples, a lot of like question 2 or 3, get used to the nuances because you want these questions coming up. Okay, it's just using a formula either to substitute and calculate or substitute and solve. Okay, so 4 things you need to do. Use the formula involving the exponential functions, so e to the power x, solve equations where the unknown is within the power, solve equations involving the exponential functions, and then context, and that last one's a big one. Okay, you'll recognise them very quickly when you're doing your past paper practice. Okay, thank you for your time.